Okay, so I guess the theme for the rest of the week is deep. This was advertised as a deep dive, and tomorrow is deep learning. Although I don't think this is going to be particularly more deep. I felt like we went pretty deep in expectation maximization yesterday, and there's actually more topics to cover here, so we have to relax and go deeper. How many people have ever used samples that came from a Markov chain? Okay, so a lot of you. How many people have actually generated their own samples? Okay, good. So that's what I was expecting. So a fair number of you have some experience with Markov chain Monte Carlo. So the way I interpreted deep is I actually want to show you some of the theory behind Markov chains, because it's pretty easy just to you get an example, you run your chains, and you're up and running pretty quickly without really having any idea of what's going on and why this works. And especially if you're kind of having a challenging problem you're trying to solve, it's just taking too long, or your chain isn't converging. It's really helpful to really understand what's going on under the hood. So we'll spend some time just talking not about Markov chain Monte Carlo, but talking about Markov chains. Okay? It's kind of a mathematical object. There's a whole nice theory behind that. And then we'll talk about Markov chain Monte Carlo, and then talk about some of the practical, the nuts and bolts. What are the packages out there? Which ones should we use? Okay, so what is Markov chain Monte Carlo? Just to set the context. So it's a computational tool. Remember that I talked about the different types of solutions. So this is an approximate solution. It's not an exact solution, and it's one where it's one that's relatively straightforward to set up and relatively expensive to calculate. The power of the reason why everyone should be familiar with MCMC is that if you're doing Bayesian inference, it's basically the only thing that is guaranteed to be able to solve your problem. Okay? You may not do it in fast enough or as fast as you'd like, but you can always use MCMC to solve basically any Bayesian inference problem. Not just the standard problem of given a model, sample the parameters, but you can also use it for the harder problem if you've got competing models and you'd like to compare them. Okay, so what is the problem that, so this is a tool, and what is the problem that it solves? So suppose you have some function of your parameters. I'm just using theta to represent the parameters. It doesn't mean we just have one parameter. We might have 100, or in the example that I showed you at the introduction lecture, I showed you someone had done a Markov chain Monte Carlo of the whole universe. So there they had millions of parameters. Okay, so that theta could encode the full density and velocity map of the universe, the delta field of the universe. Okay, so you have this function of the parameters, and it's proportional to a probability density. Okay, so by that I mean there's just some constant n, which we're turning into our probability density. So that once we've said that, then our function p is not totally arbitrary, because normalization is arbitrary, but it's still, the normalization is not going to fix any negative values here. So every value has to be greater than or equal to 0. Equal to 0 is fine. That just means there's some region in the parameter space that for some reason is completely forbidden. But it can't go negative. And then you don't know the normalization constant, but you do have to, but you could calculate it. You could just integrate over this whole thing. And you better get an answer that's not 0 or negative, and it has to be finite. Okay, so there's a couple of kind of loose restrictions on this on your function p. And the reason that this comes up all the time in Bayesian inference is often the thing we'd like to sample is the posterior distribution. Okay, remember in Bayes' rule, the posterior distribution has that pesky denominator p of d, which is called the evidence. So in that case, in a Bayesian inference, this normalization constant would be what's called the evidence. We'd have to integrate our model over all the parameters. And in practice, that's just not something that we can calculate for most useful models. Okay, but we can often write down something that's proportional to probability. So that's what we're going to work with. Okay, so let's just be pragmatic here. So let's suppose you've already written a piece of Python that when you plug in theta, this might be an array or just a value, it's going to return that function p. Always has to be greater than equal to 0, but otherwise it doesn't have to be normalized. And what we want to do is we want a tool that will let us generate values of the parameters, sometimes these are called realizations, that are sampled from this PDF. So for example, if we want to get 10 different values, we just call it like this. Okay? So what we're going to be talking about is how do you implement this function here, generate. Okay? So we'll just, each time you call it, it will spit out another set of parameters. Okay, so why is this problem important in machine learning? So this is really central to Bayesian inference, where the unknown normalization constant is the evidence that I was just talking about. And so what we do is we just take the thing that we use for p is the numerator in Bayes' rule, which is usually much easier to calculate. You just need to be able to calculate the unnormalized likelihood and the priors. And so now then you can generate you can use Markov chain Monte Carlo to generate a random sequence of parameters values. And often this is the only, or at least the most straightforward way for doing this. Okay, so sometimes there are fancier, much more efficient methods. For example, variational methods that I mentioned in the introduction. But this is, you can always fall back on this. This is a workhorse that will always do the job if you wait long enough. Okay, so once you've got the samples, if you put aside for a moment the question of how do we actually implement that generate function, once you've got the samples, this is really powerful. So for example, if you click on that link, you can download chains these are chains from Planck. So the posterior distribution that's being sampled is basically the full cosmological parameter space. So it's hard to read here. So you have like omega matter times h squared, omega baryon, h squared, the Hubble constant, things like that. So it's basically a file with columns for each one of these cosmological parameters, and it's sampling the posterior, where the likelihood is the likelihood of the observations that Planck collected. Okay, but you end up, they've done all the work, and they've also generated the chains for you, so you can download them. And this is really useful because you can just download this file with whatever it is, five columns, and then you can make plots like this, so a corner plot. So now that this is giving you confidence levels for each pair of parameters. You also, if you just make a histogram, what you've effectively done is you've effectively marginalized out all the other parameters. Okay, so it's very useful, and this is exactly what we want to do to really do Bayesian inference. We're not forced to talk about sigmas or anything like that. We actually have the full distributions. Okay, and although it's hard to plot things more than 2-point correlations, like we're showing these scatter plots, the samples encode the full n-dimensional correlation. So you can, anything that you can calculate, you can derive from this sample. So marginalization is trivial. Each histogram is marginalizing over the other 4 parameters. Each scatter plot is marginalizing over the other 3 parameters. You can also estimate distributions of arbitrary functions of the parameters. So let's say I want the ratio of this parameter to this parameter, which would be the fraction of baryonic matter. So I just take those 2 columns and I just pairwise take the ratio of each one and make a histogram of that. Okay? And automatically, you can make any nonlinear functions of the actual columns in your Markov chain, and all the distributions will come out right. In general, when you make nonlinear transformations, even though these things look sort of Gaussian, you'll end up with non-Gaussian looking distributions, and it's all correct. Then in the most general case, you can actually perform, what you're really doing is performing Monte Carlo integrations. So if you have some arbitrary function of your parameters, what you'd like to be able to do is to get the ensemble average of that function, and they're written like this, but what this really means is we want the ensemble average where the x, the parameters, are sampled from our posterior distribution. So what it means is we want to integrate the function and then weight every value of x, of the parameters, by the posterior distribution. Okay, so we don't have to actually do this integral. All we do is we just take the samples that come out of our chain and we just add them up. We add up, we apply the function to each sample, and we just take the average of the results. Okay, it's that simple. Notice how in the integral you have to have a weight term there, but here we don't have the weight term. Why is that? Why doesn't the weight appear here? Normally when you do Monte Carlo integration, whatever the integrand is, you're gonna take an average, you're gonna evaluate the integrand at each point. But that's when your points are just uniformly distributed. Okay, the great thing about the Markov chain is these points already have the right distribution, so that the distribution of these points already encodes that posterior density. Okay, so it's really you just wrap whatever function you want around the parameters, and you just average them. That's effectively doing Monte Carlo integration. Okay, so the outline. So I'm going to spend a little bit of time talking about the underlying theory, which is the theory of stochastic processes and Markov chains. Then tell you about Markov chain Monte Carlo in particular, and then give you some practical advice. And then I hope the break will fall around there. We'll see how the timing goes. And then I have an exercise, so an IPython notebook, where you're going to be working on your own, and that will take up most of the time after the break. Okay, so let's start with the beginning. So what we're talking about, a Markov chain is it a type of stochastic process? It's a stochastic process. Stochastic is just another word for random. A stochastic process is just some black box that spits out random samples. Okay, so it's black, almost black box, and it just spits out a whole sequence of numbers. Okay, each one could just be a scalar, or it could be vectors. It doesn't matter. But the important point is that there's a sequence. Okay, x2 follows x1, xm plus 1 follows xm. So in the most general case of a stochastic process, each sample will depend on all the previous samples. And so that means that the samples are correlated in the maximum possible way. So here's kind of a little Python snippet that generates a very correlated stochastic sample. So I just make a history array, which is empty. And every time I call my stochastic function, what it does is I'm going to add a random number to the history, and then I'm going to return the sum of the history values so far, or the mean or anything. Okay? So you can clearly see each number that comes out is going to depend on the full history. And the history is just going to remember every value it's seen so far. So that's an example of a stochastic process. It's stochastic because I'm adding random numbers, and it's fully correlated because that's how I constructed it. Okay, so a Markov chain is a drastic simplification of the general stochastic process. Because in a Markov chain, each point, each new number coming out of the black box only depends on the one before it. Okay? And once you make that seemingly simple assumption, a lot of things fall into place, and you can prove much more powerful results about the resulting sequences. So that's a general Markov chain. Okay, we're saying it can't depend on all that stuff. Okay, there's an important subset of Markov chains, which are what are so-called stationary. And so stationary is what you think of like it's not moving. In other words, it's time invariant. What a stationary Markov chain is that the relationship between one point and the next one doesn't change over time, right? So if you look at an early pair coming out or a later pair, statistically those are related in the same way. So a more precise statement of that is that the probability of the n plus first number conditioned on the nth number is the same as the probability for the m plus first conditioned on the mth value. So there's some conditional probability. This arrow represents a conditional probability. In the general case, it's a different conditional probability each time, where you can think of it that it depends on n, where you are in the sequence. But a stationary Markov chain is one where it's always the same. Okay, so now we've even simplified our stochastic process much further. Okay, another important property for a Markov chain is what's called reversibility. So the name of that comes from the idea that you'd like something that's time reversal invariant. We've got two different types of symmetries here. So this is time invariant, means you can shift the origin of time, it doesn't matter. And then here we're saying, so that's a continuous symmetry. And here we're talking about time reversal invariant, which means we can just flip the direction of time. Okay, so that's a little vague though. What does it mean to flip? I mean, the sequence just keeps adding on. You can't turn the sequence backwards. So really, if you want to write this down precisely, what this reversible condition means, it means that the probability from going here to here, okay, so let's say you go to a concrete value x of n plus 1, what's the probability that in the next step you'll actually come back to the point you started at? So those have to be the same. So more precisely, the probability of going to that value from the initial x is the same as the probability that the next step will take you back to the original probability. Okay, so notice how I'm defining it without actually having an arrow that goes backwards, because that doesn't really make any sense. The sequence only goes in one direction. But it's effectively, intuitively, it's basically like turning it back to think of this as it's like a backwards arrow. Okay, and then you can prove, and I'm not going to prove it here, but you can prove that if a chain is reversible, it is stationary. Okay, so it's a relationship between those two properties, but not vice versa. Okay, so stop me if you have any questions. Okay, so now let's see how well if you have an intuitive feel for that. So look at these. I've shown you here 4 different stochastic processes. Okay, they're stochastic, so you can't just look. So I've shown you for each one. I've shown you it's the same process. I've just shown you 3 different realizations. It's basically starting it over with 3 different seeds. So that's 3 different colors there. So what I want you to do is look at these for a minute, talk with your neighbor, and try and decide which ones of these are stationary, or non-stationary, or non-reversible. So you're trying to get a feel by looking at these whether these processes have this stationary or reversible property. Okay, it's not easy, and so talk about this with your neighbors. And so it's good to kind of have a visual an understanding of what visually these things should look like. Okay, the mathematics is one thing, but what does it actually look like when you look at a sequence?
If A were stationary, then you have like a continuous convergence. And if it were reversible. So this is interesting. So the question is like, if something is, which one? I think D is reversible. Oh, so I think B and C are both non-reversible, right? Because of just the. Or at least, like, if you take the things that we can do and say that, like, this is like the odds of running backwards from 3 different numbers are 0. So B and C and A are all and then which of them are stationary? I think the.
Okay, so are any of these non-reversible?
No idea.
Fair enough. Which one do you think is non-reversible?
All of them except for maybe D.
Okay. So okay, that's good. So so what we should be looking for reversibility is we want to, and we're kind of, our eye is drawn to the fact that these things all start from a similar point. Okay, but what we want to imagine making these points all be the same, and then kind of flipping the diagram around. And now, could you tell that you've done that statistically? Obviously, it won't be exactly the same pixels, but if you were to like bring these points all together, flip it around, would it look any different statistically? That's what reversible means. What about stationary? What would a non-stationary distribution? What kind of operation could you do graphically to test if it's stationary? Yeah. So if it's stationary, then you should be able to. Well, one way of doing that is just to flip it again, right? So what you're looking at is you want to look at kind of the the scatter, right, from one point to the next, because that's really, it's the conditional probability from one point to the next. Yeah.
So just a question on that, like, is a random walk is stationary, right? But it wouldn't look the same if you translated it, at least not initially.
Statistically.
Right, statistically it wouldn't look the same if you translated it.
It would.
It would.
Yeah.
Oh, I guess like once you move past the initial starting point.
Yeah. Yeah. Okay. So let's. So this one is not even a Markov chain. This is non-stationary and non-reversible. So this is just a general stochastic process. This one here is a bona fide stationary reversible Markov process. This one here is non-reversible, and you can see that because it starts to get smoother as time goes on.
Why isn't A Markov?
Because so that's a little harder to see, but I mean what we're looking for is whether each point depends only on the previous point. So you can see here there's a lot more scatter. But it's a more subtle thing because there could be two reasons for that. One is that it's not stationary, in other words, that it depends. So I tried to make this is basically the example I showed you at the beginning. It's like you're averaging all the points that came before, that's why it's getting smoother and smoother. Yeah, but it's hard to, I don't think you can just tell by looking whether it's non-stationary or actually depends on all the previous points.
So would the conclusions change if we see the same thing but the y-scales were matching? So we see that in C, for instance, it goes up to a huge number. So that tells us immediately that if you wanted to reverse it, it won't be that easy. It won't be stationary because, for instance, the mean is easily changing from one part to the other.
I don't think so, because I could change the RMS of the conditional probability, and that would arbitrarily change the scales. I don't think you can conclude anything just from the larger scale.
So yeah, the RMS then would have to be equally discernible besides the scale.
Yeah. Okay, so this is not easy, but it's good to kind of think about. You see the definitions in terms of conditional probabilities, and it becomes a lot more real when you try and actually test if you can do these things visually. So.
Hey, go back.
Yeah.
How can you distinguish between B and D?
Because here the scatter from one point to the next is very large.
Okay.
And here it's very small.
Okay. Yeah, okay, now I can see it.
But then so then if the difference is that scatter is increasing towards the beginning, what's the difference between B and A in terms of one not being? Is it just in the mathematical average? And
It's yeah.
I mean the mathematical definition.
Yeah. So I tried to make this an obvious example where it's like getting smoother and smoother to suggest that it's kind of taking an average of all the previous values. No, okay. Yeah. That's an important thing. You notice how they're all converging to the same value. Yeah. So maybe that's a clue.
Okay.
But I'm not saying that it's an ironclad. You can just tell by looking at the image.
Okay.
Okay, so I want you to build your own Markov chain. You've already done Markov chain Monte Carlo, a lot of you, but let's actually build a Markov chain. So what I want you to do is, again in pairs, I want you to build a Markov chain for the weather where you grew up, okay? So there's two steps to this. First of all, identify the main types of weather, whatever, rainy, windy, and then write down the probabilities for each possible transition, okay? So do this in pairs. So this will be pair coding. So one of you is going to be describing the weather where you grew up. And I did an example with 3 states here. Maybe you live in Southern California where basically it's only have 2 states, or you live somewhere with more exciting weather.
Right, so the state, the Markov chain is based on the
Wait, so are we supposed to write our own Markov chain, or are we just putting down probabilities and then entering them?
Yeah, we'll just write down the numbers here.
Okay. Okay, gotcha. So then, sorry, where's the coding?
Right now you're just writing down the numbers. Yeah, so it's going to be like table.
So we want to basically make that array.
Okay.
What was what about was it interesting or
Rain about 90% of time.
Okay, so rain 90% of the time, but on a rainy day, what's the probability the next day is rainy or sunny? That's what we're trying to do. Okay, so just to make sure we're on the same page here, so the question you need to ask yourself, let's say it's raining today, what's the probability that it's raining tomorrow? Or lightning or snowing, okay? And those things have to add up to 1, okay? Because tomorrow is going to happen. It is going to have some weather.
for sunny? This was just made for Seattle where it's never sunny. So we want to make it
Yeah,
better.
it's fine. If we do UK, then it's raining on one day. It's relatively raining the next day.
So I can either take the rain.
Genuinely the same like the let's just do 80%
The exercise doctor.
UK.
Okay. Oh, okay.
If it's raining one day, then I'm just like that because it says
So it's 0.8 and then 0.8 to 0.20. And then
if
but the
it never snows, so that's just
well, if it never snows, then it's
It's an
still.
example. You don't have to use those weather
Oh,
states.
it's gonna do that.
Okay, because those are weird.
What about sun?
Those are like weird weather.
Okay, so I mean, don't overthink this. We're just writing down some numbers here. I just want you to realize kind of what are the inputs required to specify.
So the first number can be
Markup change.
Raining one day.
rain to rain is 0.
It's raining one day, it's raining another. Then we can do overcast or
0. There's like a point.
No, I think
There's like a
it has to be 2.5 and then it's now it's raining.
Okay.
You didn't have to use those weather states. That's the ones icons I can find. That's okay.
I got it.
You can change it to sun.
So
I'm gonna make it
if it's overcast, is there like is the chance of it raining equal to the chance of it
So to start says, so.
No, I think it's in the overcast.
This is the population.
So then maybe the first row.
Okay, so someone put your hand up if you have your table written. Okay, so I want you to read out your numbers. What are they?
5, 0.25, 0.25, and the next one is 0.4, 0.5, 0.1.
We discovered you can't say 0 point, it doesn't like that.
Oh, and then 0.4, 0.1, 0.9.
So unfortunately, it doesn't give the nice weather icons that I had here. Okay, but what we've done is so that you can just plug in any matrix here, and so we've now created a Markov chain. This is a generator of Markov. It's a nice visual generator. So each time the thing moves, that's going from one day to the next. Okay, and so it's turned the probabilities we have in there into so from each state here. So let's say this is the lightning state. The thickness of the arrows tells you the probability of the different transitions. So all of the orange ones are the transitions from this state. Those all add up to 1. It has to go somewhere from one day to the next. Okay, and so this is now just it's a realization. It's generating random Markov chain. So this is a fun thing. And this thing is actually created with D3JS. It's using a nice thing called forced layout. See how you move it around. So each of the links is actually a spring, and it's actually calculating Newton's laws to do this. So it kind of shows you the power of D3JS, which is a lot of fun to work with. It has a really steep learning curve. Okay, so another activity. So I just want you to discuss this with your neighbors. Is the sequence of letters in a book a Markov chain? And then the other question, is the sequence of words in a book a Markov chain? And just to remind you, the definition of a Markov chain. So in the first question, these would be the letters. So if your book starts the Quick Brown Fox, this would be T-H-E, right? And so the rule is that n+1 letter depends only on the previous letter.
So no, it's definitely no. It's something like well, the sequence of letters definitely is in the Markov chain because the more letters you set down in a word, the more you fix the probability of the next letter, right? If you have a long 10-letter word, when the first letter you might have a random chance, but then once you choose 3 letters, that eliminates a large swath of possibilities of words that are lost. So it's definitely no in the sequence of letters. In the sequence of words, it's in the Markov chain because there's narrative structure.
Yeah, and in a sense, it's more fundamental than
you can't fix the grammar of a sentence just from word to word.
Because like if I say I or I am.
Like if I have
All of the valid transitions
had
I, but they depend on
the blank. The answer is Matt.
I guess they also depend on
the chance that the word Matt comes after just the without considering all this is so much lower than the chance that the word Matt comes after the cat sat.
Yeah, it's cat.
But the word right,
that's the way it's
Okay, so what do you think here? Is the sequence of letters a Markov chain?
No.
Is it approximately a Markov chain?
No.
What would be the test? What would be like just an empirical test of whether it's approximately a Markov chain? We'll just try it, right? Let's put in some probabilities, run the Markov chain, just like we did the weather, and see what comes out. We can generate text. If we assume that it's a Markov chain, we can generate some text and see, well, does that look okay? Okay, and you can do the same thing with the words. Suppose it were approximately a Markov chain, would it be a stationary Markov chain? So what that really means is the probability of H coming after A the same as the probability of H coming after T? You get THs all over in English, right? But not after A very common. So it wouldn't be a stationary Markov chain, but maybe it's a Markov chain. So this is actually fun that you can actually go pretty far in synthesizing natural language using Markov chains. So both of these are approximately Markov chains. So I show you there's a link here which shows you randomly generated words. Yeah, here we go. So procedural name generator using Markov chains. So now you need to get your frequencies from somewhere, right? So what you need is in natural language processing, the data that you train on is called the corpus. Since they're all fancy linguists, they use Latin for everything. So here our corpus is just the names of animals. Okay, but you can pick any different things you want. So we feed it. So we're going to calculate, just measure the probability of one of each letter coming after its previous one from that data. Okay, and now let's generate some random animal names. Okay, a raccoon, a giantelope, Miss New York. Iguana. Okay, those don't sound crazy. If I told you, oh, but there's something, some rare creature in the South American jungles, and it's called a alligator, So these are not just random letters, right? This is not just gobbledygook. They actually read like words, and they actually sound plausibly like animal names.
So this is training on creating new words. What about like sentences and paragraphs?
Okay, so
Because
that's
there's a great, like,
okay, I'm going to show you that in a second. Okay, but I mean already, so this is it's surprisingly good. Just using the Markov chain. Okay. So you can go on and actually generate complete text, but it turns out to really do this properly, you need to use a stochastic process. So you need to use information from not just the previous word, from the words before, and this works really well with letters and also with words. So I put a link here, which is a lot of fun to read. I'm just going to give you one example here of what came out of this. So this is just making a stochastic training on. This was actually trained on the complete source code to the Linux kernel, and this is what it generated. This is an example of just random letters generated by that thing. Okay, it's pretty good if we actually would compile it. So this is C, not Python. So just by ingesting every single character in the source code to the Linux kernel, it learned how to generate random code like this.
Was that letter to letter or word to word?
Letter to letter. So it doesn't know anything about, that it doesn't know that return is a keyword in C. Okay, it just learns that. Okay, but clearly you have to use more than just the previous letter for context there. And so the way, if you want to do this, what you do is this is an application of a type of neural network called the recurrent neural network.
No, really. Does it, like, what about a space? Does a space consider?
Yeah, good question. Right. So once you get into the nitty gritty, you have to things like punctuation and space. You need to treat those like another letter. So it actually learns where the spaces go. It learns that you don't usually have two spaces after.
But then, like, after a space, doesn't the chance of the next thing depend on the word before?
Right. That's why you can't use a Markov chain.
Okay. Yeah. It's not a Markov.
Yeah. So this is. So often the first thing to try is a Markov chain, and if that's not working, then you need to do something more history. And the practical way to train that is using this thing called a recurrent neural network. So I recommend you look at this. There's a really hilarious. They trained it on a whole bunch of papers, math papers, and so they actually generate, and they trained it actually on the raw LaTeX source. So it actually generated correctly formatted LaTeX, and if you read the papers, they're hilarious. I can't tell the difference between the real papers and the random ones. So. Okay, so in all those examples so far, we've been working in a state space. That's basically the set of all possible values that can come out of the stochastic process. We've been working in a finite state space. Okay, we had 2 or 3 types of weather. Although there's a lot of words in the English language, it's still a finite number. But typically in scientific applications, our state space is going to be they're going to be real numbers, which means that they're not just infinite, but they're uncountably infinite. So unfortunately, we have to abandon the nice representation with the matrix of transition probabilities and the visualization of a graph showing you the chain in action. It also gets more complicated because the output values can be multidimensional in general, like in the Planck cosmology parameter, that was a 5-dimensional parameter space. In the Sloan galaxy reconstruction, that's millions of parameter dimension space. Okay, but the important point is that all of the essential elements of Markov theory carry over from the simple finite case to the infinite multidimensional state space. Okay, so in practice, when you have a Markov chain, it's going to be specified by 2 probability distributions. First of all, you have to specify how you're going to get your initial value. That's one probability distribution. And then you need the probability distribution that will take you from one value to the next. So here, for example, is a really simple, I've written it as a Python class. So this generates a stationary Markov chain. So stationary meaning that thing there doesn't know where in the sequence it is. Okay, so in the constructor, I generate the initial point just by getting a random value, and then in the generate method, what I do is I add another random value. So these two things in red, those are the two probability distributions that I've selected. Okay, and they're independent of each other. You can choose, you can kind of mix and match wherever you want. But there's two separate probability distributions that are going to determine what comes out of your chain in terms of its statistical properties. So, and the a remarkable thing, and this is really where the power of Markov chains comes in, is that if you have a stationary Markov chain, okay, meaning that arrow number 2 is the same wherever you are in the sequence, then your chain, your Markov chain, is eventually going to reach an equilibrium distribution of states. Okay, so that's a mouthful, but it's really easy to see in these pictures. So what this axis here shows you the initial value. So I only have only 10 possible states in this system. So it's going back to a finite system. This shows you the initial value, and this shows you what happens after one transition. So this is basically just a colorful way of showing that matrix that you put in for the weather. It has to be square. The numbers along each row have to add up to 1. So this is after one transition. This is after 2 transitions, 3, 4, 5. And what you see is that very quickly you get these vertical stripes. And what that's telling you is that you're going to end up, the probability of being at different states, so think of these as different types of weather, the probability of different types of weather after 5 days doesn't depend on what the probability was last week, or on what the weather was last week. Okay? So these things, here, this is just I use different random numbers for the initial transition probabilities, and again, they very quickly get into this wallpaper pattern. It's a different pattern, but what this is telling you is that once you've specified the probability of the initial distribution and the probability of the transitions, those two ingredients, as long as it's a stationary Markov chain, you will get into some equilibrium distribution. Okay, and that turns out to be really powerful. It also doesn't depend on how you start things off. So here, I'm running the same transition probabilities, but here I started off with all states being equally likely. Here I started out with only the first 5 states being equally likely, and here the last 5 states being equally likely. Again, as I go through just 4 steps in this case, I end up with a distribution. So this is the probability of being in each state. So starting from very different initial probability distributions, I end up in the same probability distribution. So this is just another way of looking at those vertical stripes, but they're the same. It doesn't matter what the initial probability distribution is. So that's telling you, although there's 2 kind of distributions you have to specify, it's really just the transition probabilities that matter. Okay, so just to summarize, once you specify transition probabilities for a Markov chain, a stationary Markov chain, you now have an easy way to generate random samples from some distribution. There's some equilibrium distribution. Okay, but that by itself is not useful. To be useful, what we want to do is we want to be able to specify the distribution. We want to be able to say, I want this particular wallpaper pattern. But in order to do that, you need to solve a tricky inverse problem. Right? You need to be able to, given the pattern you want over here, you need to know what set of probabilities to start with in order to get that pattern. And so what you want to be able to do then is, you have a target distribution. You want to select the initial probabilities, and in the language of MCMC, we don't talk about transition probabilities. We should talk about an update rule, but it's just a way of encoding transition probabilities. Okay, so a surprising fact is that I kind of made a big deal about stationarity and reversibility. It turns out that all practical MCMC algorithms actually do not use stationary Markov chains. So why do we care about those properties? Because what we do is we carefully construct our uprate rule or our transition probability so that we're going to have a chain that has similar properties. And all practical methods of MCMC are all special cases of this kind of general algorithm called METROPOLIS-HASTINGS Green. So these are 3 people that never worked together. They each kind of added their own part to this. the formulation of this MHG algorithm is done in kind of very formal mathematical language. It has some, there's a lot of subtleties to it. It uses measure theory. So I'm not going to talk about that. What I'm going to do instead is to talk about this subclass, which is just the Metropolis-Hastings algorithm. And then in fact, a lot of the other practical algorithms we're talking about are special cases of Metropolis-Hastings. So just plain old Metropolis, something called GIBBS sampling, and then something called Hamiltonian sampling. Okay, so if you really want to understand the most general case, you need to brush up on your measure theory and learn about this. But we get almost all the insights just by talking about Metropolis-Hastings. Okay, so just to recap, so in Metropolis-Hastings, what we're trying to do is we want to sample some target probability density. We know something that's proportional to it, this function p of our parameters, but the normalization is too expensive to calculate. Typically, our p is going to be the numerator in the Bayesian posterior, but that's not required. Nothing about MCMC requires that you think about this in the Bayesian way. Your probability density can be anything. Okay, so what we're going to do is the way we're going to get our transition probabilities is in the update method, we're going to propose an update. So whatever our current set of parameters is, we're going to propose, say, like, try this. And we're going to do that by sampling some distribution Q. Okay, so this is a new element I haven't talked about. So Q is going to tell you the probability of a new set of parameters given our initial set of parameters. So what do? You want to choose a Q in this update rule that's easier to sample than the actual probability distribution you care about. Okay? Sometimes you actually know how to sample the one you care about directly. In that case, you don't need Markov chain Monte Carlo. Okay? You just sample it directly and you're done. But generally, you can't do that. So you're going to choose some Q that's easier to sample. Notice I didn't say that looks like the thing you care about. It's just easier to sample. It turns out it doesn't really have to look that much like the one you're sampling. In practice, we almost always choose Q to be a Gaussian, or like multivariate correlated Gaussian, what we were looking at yesterday, just for convenience, because that has such nice numerical properties. And your Q doesn't really have to look, it's like P. If it does look like P, it'll make things more efficient, but it won't affect the validity of the answers. Okay, so there's kind of two fundamental approaches for doing this sample. So one is what's called a random walk. That's illustrated here. We're mentioning it like that. And there, the idea is that once when you sample from your Q, what you're going to do is you're going to use that to add to your current position in the parameter space. So we have a two-dimensional parameter space. If this is where I am right now, this is my theta n. Then this is a distribution of proposed points. So it's a cloud that's centered on my current position. That's what we mean by a random walk. Okay, you're always going wherever you are now. You're going to take a random step in a different direction. Okay, so all of your distribution of steps are all going to be centered on where you are right now. There's another approach which is equally valid, which is called an independent sampling, and that is that you always anchor your cloud of proposals around the origin or any other fixed point. Okay, so there's a lot of freedom in how you do this, but this is kind of two extremes. One you anchor on where you are right now, and one is you always anchor it at the origin. Okay, and this is kind of some pseudocode there to see what that looks like. You're sampling from the same distribution, and either you add it to your existing point or you don't. Okay, so the next part of the Metropolis-Hastings algorithm is you're going to calculate this thing called the Hastings ratio. So this is the main thing that Hastings added to the work Metropolis had already done. So it's a function of both the current parameters and the new parameters. So I kind of colored it here so you can clearly see the two ingredients. So we need to be able to, we need to know what the probability that we sampled from was, Q. And notice it appears twice. So we want to know the probability that this is the probability of going from n to n plus 1. We also have to be able to calculate the probability of the backward step from n plus 1 to n. And here we need to be able to calculate the probability distribution of that we actually want. Okay. And then what you do, once you've calculated this casing ratio, you're going to accept the proposed update. Okay, it's still just on probation of this update, and we're going to accept it with a probability here, which is basically just that ratio we calculated there, but it could be greater than 1. So we'll just, if it's, we basically clip it at 1. Okay, so what that means is you calculate this thing, and you just generate a uniform number between 0 and 1. And if it's less than this, then you're going to accept it. If it's not accepted, you're going to reject that probationary point. You're going to reject it. Okay, so that's going to happen with probability 1 minus p. And what that means, if you reject it, you're just going to stay where you are. So it's normal that a Markov chain will have repeats when you use this Metropolis-Hastings algorithm. Okay, so you will get duplicated points. Okay, that doesn't sound very random. And you can be tempted to say, well, let's just get rid of those duplicated points. But you have to leave them in because that's what ensures that you have the correct statistical properties at the end of the day. Okay, so here's some pseudocode for just calculating that ratio. So here I've shown you the same cloud. So this is the random walk proposals, and this is the independent proposals. So what do you think so in the next slide, I'm going to show you, I'm going to color code each of these proposed points by the probability that we would accept them. So what do you think that's going to look like? In this case here, I didn't tell you what P is. So P is a Gaussian centered at the origin. Okay. So the sample, the thing we're trying to sample is just a nice Gaussian, round Gaussian centered at the origin. So that kind of tells you that you would want, if you're out here, you want to get pulled back to the middle. So we want the proposal, the acceptance probability, it better be higher over here and lower over here. And that's exactly what happens. So now I've colored them with the acceptance probabilities here. So we have a really, as long if we happen to move towards the peak of the P, then we're going to be very likely to accept it, 80, 90%. And if we happen to move away, we'll be very unlikely to accept it. Okay, but this means that if we're down here at 30%, that means that 70% of the time, if we come over here, that we have a 70% chance we're just going to stay there. So we'll just repeat that point. Over here, this is a little bit more subtle. You might expect that it would be the highest probability would be in the middle. It's actually the opposite. The highest probability is around the outside. If you think about it for a minute, you realize that because our proposal is centered on the origin, we're much more likely to pick a proposal point near the middle, but we're much more likely to keep it if it's far away from the origin. And those two things cancel each other out, and effectively, when you fold in the probability of accepting, you end up with a uniform distribution of points here. Okay, so Metropolis is a special case, and it's just when you have a reversible proposal distribution, then this ratio then by definition cancels out. So now you only need to be able to evaluate the ratio of your target probability. Okay, so just to recap, what are the requirements for doing Metropolis-Hastings? You have to have something proportional to the probability, your posterior, and you need to be able to evaluate it. You don't need to be able to sample it, you just need to be able to evaluate it up to a constant. You have to come up with some proposal density, usually a Gaussian, that you can also evaluate. Technically, you only need to be able to evaluate up to constant, although you usually pick something for which the constant is easy to calculate. That's not usually useful. And then you also need to be able to sample from the proposal density. Okay, so the crucial point, though, is you don't need to be able to sample from your target. You only need to be able to sample from your proposal, and you're free to choose any proposal you want. Okay, so GIBBS updates. So I'm just going to show you kind of a graphical introduction to GIBBS updates. This is a fairly general technique, and so let's say this is you're in a, what is it, 1, 2, 3, 4, 5, 6, 7, 8-dimensional parameter space. The first thing you need to do is you need to divide your parameter space up into subspaces. Okay? So you can have each parameter be its own subspace, but you're also allowed to group together subspaces however you like. Okay, so there's a lot of flexibility in how you do this. Okay, so then next, one update is going to be broken up into a bunch of sub-steps. And you're going to have one sub-step for each subspace. So this is kind of the sub-steps showing here. In the first sub-step, you're just going to update these variables here and leave all the others fixed. The next one, you update this, leave the others fixed, and so on. Okay? So depending on how many subspaces you divide your parameters into, that's going to determine the number of sub-steps. And you just go through them consecutively like that. Okay, so now I told you which ones are going to change and which ones don't, but I also need to tell you how are you going to do them, how are you going to make the change. So what you do is you sample from the conditional probability. So you want the conditional probability of these variables in this subspace given the values of all of these. So the ones that you're holding fixed, those are what you're conditioning on. So this is for your target probability distribution. Okay, so in order to use GIBBS sampling, you need some extra information about your probability density. You don't just need to be able to evaluate it. You also need to be able to you need to know what these conditional probabilities are and to be able to sample from them. So with the first subspace, we're just going to sample from that probability distribution here. And as we go through, once we get down to our third subspace, we'll already have updated this one and this one. And so an important subtlety here is that when we come to generate a new random set of values for here, we're going to condition. We want to condition on everything else, but we'll use the already updated values of these parameters, and we'll use the not yet updated values of those parameters. Okay, and it's important to do that. Okay, and then when you get down to the bottom, now you've done one update. Okay, so we have to break it down into steps. It seems like more work, and then you can repeat that whole cycle over and over. So the main reason for doing this is that by construction, the acceptance probability is always 1. Okay? So the price you pay is you have to know what all of those conditional probabilities are, and you have to be able to sample from them. But you get this big bonus is that your efficiency is basically 100%. Okay? You're never going to get any repeated points. So you'll always be changing every value. You'll be shuffling all the values around every time. So somewhat mitigating the fact that you have to be able to do these conditional probabilities is you have a lot of freedom in what subsets you choose. So you can do individual parameters. You can make a change of variables to your parameters. You have to do a little bit of work to figure out if that's going to work for your problem. Okay, so ensemble samplers. So this is what's implemented in MC. So I'm going to tell you in a minute is really the go-to package that you should use. It's got a great name. And so it's based on this paper here by Goodman and Weir, which has some kind of unfamiliar words. So ensemble samplers with affine invariance. As I mentioned, it's implemented MC. So the ensemble here refers to the fact that what this algorithm does, instead of just generating one chain, so imagine you got kind of one person doing a random walk in a field, you actually have a whole bunch of walkers, okay? 100 or hundreds of walkers. Okay, so imagine you've got this field and you've got 100 people in it, and each one is doing a random walk. Okay, well, what's the power of that? I mean, isn't that just the same as doing one random walk for 100 times as long? So the power is that those walkers they're talking to each other. Okay, so each walker takes a step, and then they talk to each other, and they figure out where they all are, and they use that information to determine what their next step is going to be. Okay, so they're correlated walkers. If they were just uncorrelated walkers, you're just parallelizing things and not really accomplishing anything. But the key is that they talk to each other, and that's what makes this a powerful technique. Okay, so if you want to know the details, read the paper. The affine invariance is kind of a separate concept, but what it also makes this a powerful method for certain classes of problems. And affine is just a fancy word for a linear transformation, but it's a linear transformation in our, whatever the parameter, the multidimensional parameter space. And by constructing an affine invariant sampler, what it means is that your sampler has exactly the same efficiency and the same results if you make any linear transformation of the parameter space. Okay, so in particular, if you, let's say you're sampling like a really long stretched out Gaussian, you can make a linear transformation that makes that a nice round Gaussian, which would be very efficient to sample. You don't need to make that because the affine sampler will, it doesn't care that it's being stretched as long as it's just a linear stretch. So those are the two main ideas there. And each walker is basically performing a Metropolis-Hasting, but it uses this proposal distribution that comes from all the walkers staggering around this field, talking to each other after each step. Another nice thing of this is really straightforward to parallelize, so if you have access to lots of cores, you can take advantage of them. And it also doesn't require derivatives. Okay, so the importance of that is going to become clear in a minute. So the last technique I want to talk about, and this is important because it's probably the most powerful, but also the most difficult to use. So this is something called Hamiltonian Monte Carlo, and it relies on what I think is a nifty physics analogy. So recall, I put it in quotes because I'd be very impressed if you actually do recall this. But if you have your qualifiers to look forward to, it's a helpful review. So Hamilton figured out that equations of motion for an arbitrary system, you can basically put all the information about the system into this matrix H, or its operator H, and then you can write down the equations of motion using these coupled first-order differential equations. So there's two things you need to keep track of: the positions of the particles, Qi, and the momenta of the particles, P sub I. Okay, so we have many particles. And all of the dynamics is wrapped up in H. So this says that the rate of change of a position is just like the momentum derivative of the Hamiltonian. Rate of change of momentum is negative of the position rate of change. Okay, that's Hamiltonian mechanics. And in practice, many physical systems, you can simplify the Hamiltonian. You can break it into a potential energy that only depends on the position. That's going to be important. And a kinetic energy that only depends on the momenta. In particular, the kinetic energy is just p squared over 2m for each particle, and you just add those things up. Okay, so you're probably wondering how this could possibly be related to Markov chain Monte Carlo. When you have this simpler Hamiltonian, this adds up into potential and kinetic energy. You get these much simpler equations of motion. Notice how this one here you can basically just solve already, and then the only thing you don't know, basically, that tells you about your system is the potential energy U, and so it's that update rule there that's going to be a little bit more tricky. So how do we leverage this to make a Markov chain? The first thing we're going to do is we're going the Q's, the positions of our particles. Okay, we're basically going to create an artificial physical system that obeys Newton's laws. And we're going to simulate that system, its physical dynamics, in order to generate a Markov chain. Okay, so we're going to identify the positions of our particles as with the parameters. So let's say we have 3 parameters. So that means our particles are going to live in 3 dimensions. Okay, so each Qi, Qi is then will be the I indexes the different parameters. So identifying positions with parameters. But what about the momenta? So we're actually going to have to create a whole new set of parameters. So if you have 5 parameters like in that Planck chain, in order to use this technique, you need to create another set of 5 parameters. Each parameter needs a corresponding, it's like a position, and needs a corresponding momentum. Okay, so you're going to have to add new parameters to the problem. We're going to treat those as nuisance parameters. But this doesn't really look like a promising approach, because what we're doing is we're doubling the number of parameters. Okay, we originally had a 5-dimensional problem, now we've turned it into a 10-dimensional problem. Why would you want to do that? The way you make a chain is you just pick a random starting point, and then you just let it go. You just use Newton's laws to figure out where the particle goes. And the particle now is kind of representing a point in parameter space for some fixed time. Okay, so that's one update. You just randomly create initial conditions, let the physics run, and then see where you end up. And where you end up, at this point, you now ignore the momenta; those are nuisance variables. And where you end up, that's the parameters that comes out of the chain. Okay, so it's kind of a clever technique. We already, there are very efficient ways to solve Hamilton's equations like that. So the fact that you have to double the number of parameters actually doesn't turn out to be so bad.
How do you choose the form of view?
Yeah, right. So the total energy of this this system is conserved by construction. So we actually know the probability density that's going to come out. So this is just coming. This is the canonical distribution from statistical mechanics. You remember that your qualifier. So what it says is the probability of getting certain positions is just given e to the minus potential energy over kT. Okay, this is physics, so there's actually a temperature required in here. So what we do, the way we pick U, is we're going to create a potential energy, in quotes, that gives us the probability distribution we actually want to recover. So we'll pick a probability distribution that's just equal to negative of the log of the probability that we actually care about. Okay. We know our probability, and we can say, let's pretend that's a potential energy, and now I can simulate this system, this physical system, that if I just give it random starting points, it will generate positions in parameter space that have the right distribution. It doesn't matter that there is no physical system that actually has that potential energy. It's a mathematical analogy, and it's using the physics kind of for inspiration here. Okay, so we've got a bunch of hyperparameters here. We've got masses for every particle. We've got temperatures. What do you do with all those things? So in practice, you just set everything to 1. Set the temperature 1, set all the masses to 1, and it just works. The disadvantage of this method is pretty complex to implement. Don't try it at home. But someone else has already done the work for you. It also requires that you can write a function to evaluate the derivatives of the partial derivatives of your potential. And that's because, so those appear here. We need to know the partial derivative of the potential energy, which is just the log likelihood, the log posterior, with respect to each parameter. Okay, so you need to be able to evaluate all of those things. So that's an additional requirement. Just like with GIBBS, we have to be able to sample from the posterior. So that's the additional requirement here. It also, but what helps is there are some packages, very powerful packages, one called TensorFlow, one called Sienna, which you might be hearing about later tomorrow. But these are mostly these are created mostly for deep neural network learning. But they're also what's powerful about them is you don't have to write code for your derivatives as long as you use you basically write an expression. If you write an expression using the object, the classes in either of these packages, it can be automatically differentiated. So it basically knows all the rules of calculus for doing derivatives, and it will look at the structure of your code and take derivatives for you automatically. So it's a very powerful concept. It's basically analytic. There's no numerical approximations going in. But it does require you to build expressions that are a little unwieldy because you can't just use plus for the addition. You need to, well actually you can, but for things like exponential or log, you have to use their versions of those operators that are like automatic differentiation aware. Okay, so some useful links here. So there's some kind of cute people have done showed animations to compare the different samplers. So I just want to briefly show you so you know what's available, but we don't have time to kind of dig in deep and look at these. So this first one is a Hamilton. This is a METROPOLIS-HASTINGS sampler. So we're sampling. It's just a two-dimensional Gaussian, so you can see the points, how that thing walks around. And then for comparison, so this is good to get some insight into how these things compare. So here's now a GIBBS sampler. Remember, GIBBS sampler, it accepts every step, and it also updates every parameter. So both x and y are going to change every time. So it has quite a different characteristic. And then here, so this NUTS is kind of a fancy version of this Hamiltonian Monte Carlo, which is already pretty fancy. And this is what it looks like. And the main qualitative feature to get from this is that the Hamiltonian Monte Carlo sampler takes much larger steps. Okay, so it explores it maps out the space more quickly. But it's not just like going randomly out there. It actually knows, it learns pretty quickly the general features of the distribution that it's sampling. Because one thing that you'd like is you'd like there to be a lot of scatter here, because that means from one sample to the next, you don't have large correlations. So there's several packages I'm going to talk to you about. This is a useful link because it compares some of them. Unfortunately, I think the only one of these that I would recommend you use is a MC. I do recommend PyMC, but there's a PyMC3 that's out now, and it's changed a lot. That's really what you should focus on. Okay, so we should talk about metrics. Suppose you have you want to try different samplers. Should I use GIBBS? Should I use Metropolis-Hastings? Do I need to really bite the bullet and use this fancy Hamiltonian stuff? So we need to have some metrics to talk about what's to compare different methods. So an important thing that you should care about is what's the efficiency? What fraction of the proposals are accepted? Okay, if it's very inefficient, it'll just stay in some relatively high probability point, and it'll just spend a long time there. It might spend 100 updates at that one point. What's the coverage? Are you fully exploring the target density? It might move around. If it just moves around in a really small ball, but it is not exploring the full probability density, that's not good. And also correlation. And there's two types of correlation. How correlated is one sample to the next? And you can measure that with the autocorrelation length, for example. An easier way of dealing with this is just to make a plot, a time series of all the values of a particular parameter coming out. And you'll kind of see how correlated they are. So if it looks like a random walk like this, and those are very correlated, and what you'd like it to look like is more like that. So this is kind of visually you can get a feel for it. And then also you care about how independent are the samples that come out from your initial starting point. And in general, you want to prefer coverage. You have to have coverage, or else your results aren't valid. And you'd like to have low correlations over efficiency. Okay, so if you have to give up on something, give up on efficiency. It's better to get the right answer eventually than to get the wrong answer quickly. I'm just going to skip over this and just give you practical advice. So how long should the chain be? You've got something every time you're going to call this update routine. How many times should you call it? So the answer is that you need to generate a large multiple, so let's say 5 or 10 times whatever length of sequence is necessary for the autocorrelations to drop to 0. Okay, so the autocorrelation is it's like a covariance, but instead of correlating things at different positions, you correlate things at different lags. So like you look at the correlation between the nth sample and the n plus kth sample. Okay, and you look at that, and you kind of slide that along, and you just look at the correlations of all those pairs. So you need to find out over what range or lag, what time delay, that things are essentially uncorrelated. And once you know that, you need to make it 5 or 10 times bigger. That's the minimum length of your chain. Okay, so you have to do some work, and these packages don't do that for you automatically. So often people just they neglect this, and they'll just run it for just basically based on your patience. If you're willing to wait 10 minutes, you run it for 10 minutes without actually checking whether that was long enough. But if you're not sure and you want to be lazy, then one long chain is always going to be safer than many short chains. Because if you have many short chains, there's a chance that none of them is really going to be long enough. So another issue is, should you remove the initial burn-in samples? So people talk about burn-ins. So that terminology comes from electronics, where every new iPhone is put into an oven, and they crank it up to 200, maybe not 200, but they basically kind of stress the electronics, because the way electronics works is that if there's like a loose solder joint or something, it will fail pretty quickly. And then the ones that are dead after 10 minutes in the oven, they don't sell those. It's actually a bad analogy, because it doesn't really, I'm not sure how the analogy factors in here, because but the idea is that maybe because you might not have picked a good starting point, the initial 100 or 1,000 samples might be sort of burn in, and you just want to ignore those. Okay, so actually this is generally done, widely done, but I think it's mostly harmless, but it's unnecessary. Okay, you shouldn't remove burn-in, because what that means is you didn't really take the time to think carefully about your starting point. Okay, a much better approach is you do think you think about your starting point. You don't know the answer, but you should be able to pick a starting point that basically that you could live with in the final sample. Okay? So if you can't even do that, you don't really understand your problem. Okay, so I claim that you should not remove burn-in. You should just pick a value that you could live with in your generated sample. And another reason for doing this is if you pick a terrible starting point, you're asking your Monte Carlo chain to discover where the maximum likelihood point is. You need to be in the neighborhood of the maximum likelihood before the chain is going to be generating sensible samples. So you can just use the Markov chain as a brute force optimizer, but it's a really inefficient optimizer. Okay, so you have to do the work of understanding your problem and coming up with a decent initial starting point. And at that point then there's no reason to remove that starting point or the initial n samples. You don't remove burn-in. Okay, another advice you'll sometimes hear is that you should thin the generating samples. Okay, but they look so correlated from one sample to the next. So obviously, what if I just take every 10th or every 100th? That will remove the correlation. Okay, so you shouldn't do this. You can never get a better answer by throwing away information. Okay, the whole chain has the right statistical properties. If it bothers you that the sequence, the samples are correlated one to the next, then just shuffle them. Okay. So, I mean, yes, they are correlated, but that's the point. Okay, you shouldn't be doing any, none of your inference should depend on the ordering that comes out of the chain. Okay, so don't remove burn-in and don't thin. Which updating algorithm should you use? So the random walks are very robust. But they're also very inefficient. Okay, the fact that if you take a step forward, you're equally likely to take the same step backwards means that they're very inefficient at exploring the space. So basically, the theme of all the fancier algorithms is to try and suppress that random walk behavior somehow to improve the efficiency. But generally, the price you pay for that is you end up with something that's more fragile. And so the result is there's really no best killer algorithm here. You have to understand your problem, and you have to benchmark your problem with different methods. So which package should you use? So my advice is you should always start with MC. It's really easy, it's efficient for a lot of problems, it's all you need. If that's good enough, then you can stop there. Unfortunately, MC only implements this one affine ensemble averaging technique. So if you suspect that you really do need to use a different approach, for example, a Hamiltonian Monte Carlo or the GIBBS updates, you're going to have to use a different package. And then I recommend that you use this PyMC3. PyMC3 is a kind of heavier install because it uses Piano, one of those packages that can do automatic differentiation. And whatever you do, don't write your own Markov chain sampler. There's a lot of subtleties to get right. I mean, it's a great exercise, and I kind of included, if you just put together the code snippets that I had here, you would have a working sampler. So it's good pedagogically, but don't be tempted to do that. Sometimes after you do this, you've tried all this, it's still going to be too slow, and then what should you do? So if it's like an order of magnitude, 2 orders of magnitude too slow, then what you need to do is you need to look at variational methods. Like here's a good starting point here. And remember, variational methods, that gives you exact results from approximate posterior, as opposed to MCMC, which gives you approximate results for an exact posterior. But in practice, you have to do a lot of work on paper to express your problem in the right way with this. But once you've done that, then it's very fast. Okay, just leave you with some references here. So this is probably the best starting point. This is a book. It's not free online, but they do have a couple of chapters online. And chapter 1 is a really good introduction. Basically covers the same material that I talked about. And chapter 5 is specifically on the Hamiltonian Monte Carlo. This book here, I don't know why this image came out so small. It was the same size here. So, well, you probably recognize this. This is the machine learning in astronomy book. It's a little thin on the Markov chain Monte Carlo, but there's section 5.8 that deals with this. And then this is a classic book here, which has 2 chapters on MC. And this one is the whole book is available free online. Okay, so we're going to take a break now, and then after the break we'll come back, and I have kind of a longer exercise for you where you're going to build your own. We'll be mostly using MC, so hopefully you have installed that, or if you're not, it's a simple if installed. But anyway, so get up now, stretch your legs, and then after the break we'll be doing some work in the IPython notebooks.
All right, let's first thank David. And sorry, before we break, are there any questions on the lecture?
I'm sure there'll be questions once you start doing the exercise.
All right, okay, so let's break. It's